So far, we've been looking at different types of optical sensors, such as amplitude modulated sensors, phase modulated sensors, wavelength modulated sensors, and polarization modulated sensors. Now it's time to look at a very unique type of optical sensor, which is a distributed fiber sensor. So I told you previously that one of the major advantages in an optical fiber is that we can send a pulse of light down the fiber over long distances, because the fiber is relatively low loss, right, as low as 0.2 dB per kilometer. So you could possibly even go 100 kilometers and only lose 20 dB of the light, or 2 orders of magnitude of the light. So you could send pulse down the fiber, and you could possibly look at light that's backscattered, and from the backscattered light you can possibly try to learn what is happening down the fiber. So it's pretty much like when you send a pulse of light down the fiber, you are as if you are taking a flashlight and you are illuminating the optical fiber section by section, and we get to see through the backscattered light some information about whatever the physical environment is around that optical fiber. So that's what distributed fiber sensors are about, and specifically we'll look at the examples of Raman scattered sensors, and as well as Brillouin scattering based sensors. Okay, so let's go back and look at the motivation for wide distributed sensing. We already talked about distributed strain sensing, in which case, we said we may want to do structural health monitoring, perimeter sensing, and so on. But there is another class of sensors which is based on measuring temperature along the length of the fiber, and these are called distributed temperature sensing. And one very nice example of that is oil and gas exploration. So when you do oil and gas exploration, especially when you drill a pipe and you try to find out what is a level with which oil is present. Here you are tracking the depth, so this is actually the ground level, and then you are going deeper down the well, and here you are tracking temperature. So as you go further and further down, you will find that the temperature is increasing, and then beyond a certain point you will find that the temperature is going beyond a certain value, and based on that temperature you can actually figure out what is the level of oil present in that well. Okay, so this is called downhole monitoring, and that's very commonly used in oil and gas exploration. Similar sort of information can be very useful for another application, which is power monitoring distribution. Remember, we talked about the example of a smart grid, and we said it would be nice if we could monitor the transmission or distribution of power along those electrical lines, and that is possible if along with the power cable you have an optical fiber embedded. So what do you see in this case? This is actually temperature as a function of distance, and you know that whenever you are transmitting power through electrical cable, due to Joule heating, you will end up having a rise in temperature. So you expect the temperature to rise to a certain level, but then you may see things like this, see these spikes over here, which are indicating that there may be some faults in the power cable. So by having a real-time monitoring of the temperature as a function of distance, you can actually figure out if there are some damages in the insulation or some corona discharge that's happening, and you know, faults like that. So for real-time power monitoring, distributed temperature sensing is very useful, and what we will see is this is actually enabled by distributed fiber sensors. Okay, so let's go on and look at the principle of distributed fiber sensors. Before I explain the specific principle of distributed fiber sensors, let's see what we can do for some of these applications that we talked about using known technology. We did talk about fiber Bragg ratings, and so why can't we use fiber Bragg ratings for such applications? Sure enough, you know, we talked about it. You can actually have different different gratings with different periods and different sections, and then we'll be able to pick up whatever perturbation. In this case, you want to get temperature information along the length of a pipe, let's say, or length of a cable. Then you could put multiple gratings down the line, and you could possibly pick up the temperature information at these points. The only problem with this is fiber Bragg rating is essentially a point sensor. So it only provides information at that point. It doesn't tell you what's happening over here, what's happening over here. So between gratings, you do not know what is actually happening. So this is not a true distributed sensing solution. So that's why we call this as a quasi-distributed sensing solution. Now, what would a true distributed sensor look like? Well, a true distributed sensor would look like this. Now, you have an optical source, and you know, you may want to send some light, and that, as it propagates down the fiber, is going to send some Bragg scattered light all along the length of the fiber. So you should not have to say predetermine this is where I'm going to look at. Like, if you know exactly where you want to look at, and if you need only tens of sensors, then fiber Bragg ratings are probably good enough. But if you want a true distributed sensor, that is, wherever the fiber is going all along the length of the fiber, you want to pick up physical parameters like strain and temperature, then you essentially need a solution like this. So what do you do in this? Well, you actually send a pulse of light. Okay, instead of so far we've been looking at all the other cases where it's a continuous wave radiation that's sent into the fiber, but in this case I'm sending a pulse of light. You know that a pulse of light is extending over a certain time, and that actually, when it's propagating down the fiber, is occupying a certain section of the fiber. Okay, so and it's going to propagate all along the length of the fiber. So this is what I was talking about. This is like illuminating section by section by section of the fiber, and then you can look at the backscattered light. The backscattered light, you can actually look at it as a function of time. Okay, and so why would that? So what would that give us? Well, we know that the light actually travels in this fiber with a very specific velocity. Okay, the velocity is given by velocity of light in free space divided by the refractive index of the medium, or the refractive index that the light sees as it's traveling down the fiber. So that would be the velocity of the light. So if you know the velocity of light, you can convert this time, right? This time multiplied by the velocity of light will give you distance, right? Now, of course, you have to be careful about this. The light actually goes down the fiber and then it comes back. So it's actually going through a round trip in terms of actually distance. So you'll have to when you convert this signal as a function of distance, you would have to be taking care of that. But nevertheless, if this pulse is going down the fiber, as it's propagating down the fiber, it's going to send some backscattered signal. Let's say the intensity of the backscattered light is looking like this, and that might actually indicate that there are some perturbations happening at these locations. So that is actually what we mean by a true distributed sensor, because in this case the perturbation can be anywhere along the length of the fiber, and because the pulse is actually traversing along the entire length of fiber, you get to find out what is the backscattered signal at any point along the fiber. And like I said, this can be converted, the x-axis can be converted to distance, so you get a clear map of the perturbation that's happening in the fiber. Okay, so let us actually look at how to make an instrument that can capture this backscattered signal precisely. And one aspect of light that helps in this process is the fact that when light actually goes through any medium, let's say it's a reasonably transparent medium, okay, several things can happen. The light can actually, of course, propagate down the fiber, get transmitted, but some part of the light may even get absorbed within that medium, but part of the light also gets scattered. Okay, so why does it get scattered? Well, there's one reason where the optical fiber, you can look at it as having density fluctuations all along the length of the fiber. That's the way the fiber is made. It's a highly amorphous material. So you have scattering all along the length of the fiber, and that scattering is what you call as Rayleigh scattering. It scatters at the same frequency or the same wavelength that it went into the fiber. So it's called elastic scattering. And so there is no transfer of energy. Light just goes in there and it gets scattered, and we are looking at the backscattered light. Now that happens all along the length of the fiber. But it can also get scattered by what are called phonon modes, some vibrational modes that are existing within this material, what is called acoustic vibrational modes. So those are like the whole glass network is sort of agitating at room temperature, and so that causes some vibrational modes, and those will actually could possibly interact with the light, and you can actually get scattering happening, which is called Brillouin scattering. Now there is another process that can happen. If you go at and look at this material at a molecular level, the molecule consists of two atoms attached with a bond, and the atoms are moving around their mean position, which means that there is some vibrational mode corresponding to the molecular itself, corresponding to the molecule itself. And that vibrational mode can once again scatter this electromagnetic radiation, this light radiation, and that scatter can produce what is called this Raman Stokes or Raman Anti-Stokes. I'll go into more details in the following slides. But the key thing to note is that this is not very high probability. Typically, when you're talking about Rayleigh scattering, we are looking at 4 to 5 orders of magnitude lower compared to the light that you went in with, and Brillouin scattering is it's almost within an order of magnitude compared to Rayleigh, but Raman scattering is much less probable, and correspondingly, when you look at the backscattered light, that could be 6 to 7 orders of magnitude lower than the incident light. So these are very, very faint scattered signals. So this is why, whenever light goes through any of these materials, you may be having Raman and Brillouin scattering, but you're not normally seeing those because these are very, very faint sort of backscattered signals. So unless you're looking for it specifically, you may not see it. Okay. So let's first look at Rayleigh scattering, and let's see how to make an instrument which can characterize the loss of the fiber. Let's say you have a long length of fiber with multiple bends and connectors and so on. How do you actually get information about that fiber by launching light into the fiber? Okay, that's through a instrument that's called optical time domain reflectometer, and I'll talk about that in a minute. So what is optical time domain reflectometry all about? Well, you could essentially take a laser and launch light into an optical fiber, and let's say you send it through a coupler, a device which sends light from this port to this port. But whatever backscatter light, part of the backscatter light is actually coming through this port, and you can actually observe it using a optical receiver. Okay, so if you send a pulse of light, okay, that pulse is going to occupy a certain section of the fiber, right? And whatever scattering that could happen within that section of the fiber will actually come back towards the detector. So this is actually an illustration of how light is scattered from this section of the fiber. So it's going to take a certain time, right, to go for this pulse to go here, and then the scattered light to go back to the detector. Okay, but it's all very well timed, meaning it's all highly deterministic, because you know what is the velocity of light in the fiber. But the point is, if you send a relatively large pulse, you get a relatively large backscattered signal. Okay, so your signal to noise ratio could be fairly good when you send a pulse like this. But the downside of that is, if you have two perturbations, two events as we call it, that are fairly close with each other, meaning they're spaced it's a shorter distance compared to the section that the pulse is occupying, then there is actually no way of telling that there are those two events. Okay, so you're not going to be able to resolve these two events. Okay, if you want to resolve those two events, what would you do? Well, you could actually go with a shorter pulse. Okay, if you have a shorter pulse, so that it's occupying a distance that's lesser than the smallest distance you want to resolve in the fiber, then you could potentially resolve these two events. But what is the disadvantage of that? Well, the disadvantage is that because the fiber is occupying a smaller section, the amount of scattering that happens within that section is also lower. So the signal that you get back is going to be lower, and if you have a constant noise floor at your receiver, that means the signal to noise ratio is not going to be very good. And if the signal to noise ratio is not very good, then the accuracy with which you can actually detect these events may be compromised. Okay, so this is actually a classic trade-off as far as optical time domain reflectometry is concerned. If you want to actually get signals from longer distances down the fiber, you want to actually go for a fat pulse, a nice wide pulse, okay, but you don't get very good spatial resolution in that case. But if you want high spatial resolution, you need to send a thinner pulse, meaning a short pulse, and in that case you're not going to be able to go very far down the fiber, or the signal to noise ratio that you get at a farther part of the fiber is going to be quite low. Okay, so it's always a trade-off between the signal to noise ratio and the spatial resolution that you can achieve using this optical time domain reflectometer. Just keep that in mind. We'll come back and look at that a little more detail. So how do you put together an instrument? Well, you start with a signal processing unit, something that triggers a pulse, okay, and then that this driver actually gives a current pulse, and the current actually drives the laser so that you can get an optical pulse out of that. This optical pulse, you will send it through a coupler, a device which sends 50% of the light down this fiber, okay. And then as it propagates down the fiber, you will typically have scattering all along the length of the fiber, okay. But because of the fact that you are losing light due to this scattering, the light is getting attenuated, the amount of light scattered from this region is going to be lesser compared to the amount of light that's scattered from this region, and that is going to be still the amount of light scattered from this region is going to be still lesser than this one, and so on. So what you expect to see in the backscattered intensity trace is you will have a good reflection because of this connector, which is actually two fibers with an air gap. Whenever you have an air gap, that's like a impedance mismatch, so you will have what is called a Fresnel reflection, so you get a reflection of the pulse. And then when you look at the backscattered signal, this is the Rayleigh backscattered signal, is going to keep going further and further down because of the fact that it's getting attenuated as it propagates down the fiber. This is the 0.2 dB per kilometer attenuation that I talked about previously, right? So, and of course, whenever there is a splice, there is a bend or whatever, at that point you're losing further light, so you will have a sudden change in the level, and then on the other side once again you have this Rayleigh scattering happening, so you have this attenuation, and then further down you have even more loss and so on. And here at this connector you have a back reflection, a Fresnel reflection, so that's why you see like a pulse, and then further down it goes down like this, okay. And finally it reaches the noise floor, so you're not going to be able to see any signal once it gets to the noise floor, okay. So how do you see all this signal? Well, basically whatever is backscattered, you extract that through this coupler. A part of the light is coming over here, and that light you make it incident on a photodiode, which can be a PIN photodiode or avalanche photodiode, and the output of the photodiode is going to be a photocurrent, and that photocurrent is converted to a voltage using a low noise amplifier, typically a transimpedance amplifier, and then the output of that is going to be digitized using analog to digital converter, and then it's going to go back to the signal processing unit. And this is where the signal processing unit is going to be important, because you shoot one pulse and then you start listening, okay. You're listening for the backscattered light. In this case you're detecting the backscattered light. It's like what you do in a sonar. You send an acoustic pulse and then you look for backscatter light, very much like what bats do, right? So they navigate by sending sound waves and looking at how long it takes for the backscatter signal to come back, and based on that it actually says okay, there is some obstacle close by and so on. So it's the same principle, right? So you are actually looking at all the backscatter light. So you wait until the light goes through the entire length of fiber and comes back. For example, if you send a pulse of light over 100 kilometers, it will take roughly 1 millisecond to go and come back, okay. So you wait until then, and then you could send another pulse, because within 1 millisecond none of this fiber characteristics have changed, so you could potentially send another pulse and get signals once again and so on, and that might actually be helpful to improve the signal to noise ratio. I'll come back to that in a minute, okay. But let's actually look at the level of light that's coming back. So to really see what is the dynamic range of your instrument, that is how much of the signal can you get over what distance. You have to look at a map like this. This is actually power as a function of distance. So this is, let's say, is the launched power, right? So let's say 100 milliwatts of power you launch into the fiber. As it propagates down the fiber, it's going to lose some of the light because of the intrinsic attenuation in that fiber. That's actually, let's say, it's 0.2 dB per kilometer, so it's going to keep losing light as it's propagating down the fiber. Now what we are interested in is the backscattered power, and this is actually defined by the Rayleigh backscattering coefficient R. So it's going to be, say, 30 dB or 40 dB lower compared to the launched power. So you will have the backscattered power, that is also decreasing because the incident power itself is decreasing. But pay attention to this. The slope of this is higher than the slope of this. In fact, to be precise, the slope of this red line is going to be twice compared to the slope of the blue line. Why? Well, this is just tracking the power that's going down the fiber, whereas this is tracking the power that's coming back also. So while going down, it loses some light, but on the way back also it's going to lose light at the rate of 0.2 dB per kilometer. So this actually will be twice the slope of this one. And of course, what you can see coming back is going to be limited by the noise at your receiver. So let's say this is the level of noise that we have for our receiver. Then up to this point, I can see what is happening. Beyond this, my signal is submerged in the noise, so I cannot see that. But on the other hand, as I mentioned in the previous graph, we have a possibility of sending further pulses and improving the signal to noise ratio. So how do you do that? You send another pulse and you get the backscattered signal. Then you add that to whatever you got for the first pulse, and then you send another pulse and then you get the backscattered signal, add that, and so on. So when you add all these signals, the signals, if you say n times you have sent these pulses, n pulses you have sent, and you've gotten signals back. The signal amplitude goes as n, okay, whereas the noise, when you look at it, the noise variances add, but when you talk about the RMS value of that, that is going to be root of n. Okay, so the noise, actually the noise floor increases. It also increases because every time you are accumulating noise, it also increases, but that increases only at root of n, whereas the signal increases as n. So overall, the signal to noise ratio improvement you get is root of n, where n is the number of pulses that you have sent, or in other words, the number of averages that you have done. So if you do that, you can actually effectively reduce the noise level, and that means this backscattered power is meeting the noise floor at this point instead of this point. So you have managed to unearth this much of the signal, this much distance. So you have improved the overall distance over which you can get this signal. And this actually is called the dynamic range, from the point you start seeing the backscattered power to the point it disappears into the noise. Okay, that is called the dynamic range of the instrument, and that's actually a key parameter that we look at when we design this OTDR. Okay, so let's quickly look at how to improve the signal to noise ratio. Like I said, the signal to noise ratio goes as root of n, where n is the number of pulses that you have sent, or the number of averages. So to illustrate that, here is a typical OTDR trace. This is the backscattered power as a function of distance. What you see in the green is what you have gotten after just one pulse. Okay, So the signal is going into the noise even at about 30 to 35 kilometers. So you cannot see the signal beyond this point. But you send further pulses, 1000 pulses, and then you keep accumulating the corresponding traces. This is where the signal processing unit is very important, because it has to synchronize all these functions. And if you do that, that's what you get at the blue trace, 1000 averages. You are able to improve the signal to noise ratio, which means that your noise floor effectively has come down. With 1000 averages, you should see a noise floor improvement of roughly about 15 dB. So that's almost what you see over here, and correspondingly you are able to see more of this. You are able to see up to maybe 60 to 70 kilometers the signal, the backscatter signal. And then of course you can keep doing this. Now if I go to 64K averages, then I get even better signal to noise ratio improvement, and the noise floor goes even further down, and then I can see even longer length of fiber. So this is actually a very interesting trick that you use to improve the dynamic range of your OTDR. And this is made possible because to do this 64K averages, guess how much time I have taken? For one trace, I have taken 1 millisecond if I am going over 100 kilometers, right? In 1 millisecond, the light pulse goes to the end, and whatever backscattered comes back within 1 millisecond. Now, if I do 1000 averages, that's 1000 milliseconds, that's 1 second. So I managed to improve the signal to noise ratio in 1 second by this much. And then if I wanted to go 64K averages, that's 64 seconds. So that's just 1 minute. So what is happening within 1 minute? Not much. What if you're looking at what is happening in optical fiber over a minute, the environmental changes are not so great. The loss certainly doesn't change so rapidly. So you could easily take a minute or two to do this measurement, and in this process you got a huge improvement in the signal to noise ratio, and through that the overall dynamic range. So this is actually a very, very powerful concept that is used in OTDR to improve the dynamic range. Now the other thing you could do is also try to use an avalanche photodiode to improve your signal. So essentially we know that or something that we will look at in more detail is a PIN based receiver, especially when you're considering for an OTDR application, is typically limited by a noise called thermal noise that's happening in the receiver. Now if you go to an avalanche photodiode, you actually incur what is called a short noise, but because the short noise to start with is very low, you can actually keep getting an avalanche gain without significantly changing the noise floor. So in this case we got an avalanche gain of about a factor of 20, and so that corresponds to 13 dB, but then again you get only half of that because of the fact that it's actually a round trip backscattered signal transmission that you are getting, so you have to account for that. But I mean, rather this is actually 11.2 dB improvement divided by 2 is what you get as 5.6 dB. So you could get better dynamic range by using a photodiode which has an internal gain. That's what an avalanche photodiode is. So you are able to improve the overall dynamic range. Okay, so that is what we have as far as OTDR is concerned. But the OTDR right now, based on the Rayleigh scattering, is only giving you information about loss in the fiber. What is the rate at which the signal is getting attenuated, and if there are any connectors or splices, what are the losses in those points, that's what it gets. Remember what we started talking about is distributed temperature sensing. So let's see actually how to implement distributed temperature sensing using this OTDR concept. Okay, so essentially we need to marry the OTDR concept with something else. What is that something else? That is what we are talking about as Raman scattering. Okay, so what is Raman scattering? As I mentioned briefly before, when you have an incoming electromagnetic radiation interacting with the vibrational modes of the medium, which are called the optical phonon modes, then there are two different events that are possible. One is it can give energy to this vibrational mode, in which case it scatters off with lower energy. So this is what we have indicated here. This is the incoming photon energy, but part of it is given to this vibrational mode, and it scatters off with a lower energy photon, and lower energy corresponds to longer wavelength. So that's why I have indicated incoming as green and the scattered as red. Okay, just to keep track of the wavelength. But there is also another event that's possible. That event is it can suck the energy from this phonon mode and scatter off with a higher energy photon, right? And that is what we call as an anti-Stokes process. Now that's what is indicated here. If you already have a vibrational mode with a certain photon energy, you can suck this energy with the incoming photon, and you can scatter off with a higher energy photon. Okay, so you want to ask the question, under what circumstances is this more probable? Okay, well, one reason why you might actually have this vibrational mode or lots of these vibrational modes, these phonon modes, is because of the ambient temperature that the material is experiencing. If you heat up the material, then all the atoms are going to bounce around their mean positions, and so you're going to have lots of vibrational modes, and in that scenario the probability of this process happening is higher, right? So as you increase the temperature, you can expect more and more of this anti-Stokes scattering happening. So if you take the ratio of the anti-Stokes scattered light intensity to the Stokes scattered light intensity, that actually comes through a Bose-Einstein distribution, but it falls out as having this exponential dependence on temperature. Okay, here delta nu corresponds to the delta nu of the phonon. The phonon h times delta nu corresponds to the phonon energy of the material. But the key point is it's got an exponential dependence on temperature. So by observing the backscattered light intensity for the Stokes as well as the anti-Stokes, taking the ratio of these two intensities, you can get a very good idea of what is the temperature at any point along the length of the fiber. So now you marry this concept with your OTDR concept, and what you get is a Raman OTDR. So how does a Raman OTDR look like? The typical setup is like this. Just as before, we have a signal processing unit which triggers a pulse. The laser driver gives a current pulse, and the laser actually gives an optical pulse. That goes through a circulator. A circulator is a device which takes light from this port and gives it to this port, and whatever comes back is actually directed to this direction, to this port. So it launches the pulse of light down the sensing fiber, just like we saw previously the OTDR concept. It goes all along the length of the fiber and gets backscattered. You have Rayleigh backscattering also, but in addition you have Stokes and anti-Stokes generated all along the length of the fiber. Was it available in the previous case also? Certainly it was available, but we were not looking at that. We were looking at only the Rayleigh scattered signal, because that is much higher intensity than the Stokes or anti-Stokes. So we were neglecting that information. But if you put a band pass filter which actually separates out the Rayleigh from the Stokes and the anti-Stokes, then you can actually extract the Stokes and the anti-Stokes, and then you can send it through corresponding photodiodes. This is actually a 2-channel receiver, so it keeps that information, and then it digitizes all of that and gives it to the data acquisition system, which is typically like a FPGA based board. That's what we have actually developed. This is an instrument that we developed in our lab. This FPGA board is able to do this entire synchronization as well as the data acquisition, and it will also help us capture the Stokes and anti-Stokes time traces, average time traces, and it gives it out, and you can take a ratio of that to get the temperature. So for example, we have demonstrated that we could pick up to 0 to 100 degrees centigrade over 10 kilometer length of fiber. That's a fairly long length of fiber with 1 degree accuracy, and in this case, because the receiver bandwidth was limited, we could achieve only 8 meter spatial resolution, but other people have demonstrated that they could do 1 meter spatial resolution. So imagine this is like 10 kilometers with 1 meter spatial resolution. Once again, it's almost like putting 10,000 thermistors. You concatenate all of them, and whatever information you can get with them, that information you get with a single strand of fiber. And that fiber is just connected to a small box like this. Each of these holes is like an inch wide and inch, distance between them. So you're looking at a fairly compact box with which you can get all this information. So that's a fairly powerful technology. So this is the kind of map that you get after some processing, basically temperature as a function of length. And we basically put a test fiber inside an oven, and we cranked up the heat of the oven, and the instrument is able to beautifully bring out the temperature of the fiber at different settings of the oven. One thing to note here is there is a certain noise at the baseline, right? So that is corresponding to the noise that you have at your receiver itself, and interestingly, we see that the noise is actually increasing as you go to larger distances. That's essentially because of the fact that from these longer distances, the Stokes and the anti-Stokes scattered signal are going to be so much lower in intensity from at this point compared to this point, right? Because the fiber inherently is attenuating light as the pulse is propagating. So because of that, you have very low level of light, and because of that, the signal to noise ratio is poor, and because of that, you do have higher uncertainty in the temperature measurement over here compared to here. So this is actually a plot of the RMS temperature error as a function of distance, and what you can see is clearly as you go to longer lengths, you will actually have higher errors with respect to your temperature measurement. Okay, so that is actually what we call as Raman OTDR, or distributed anti-Stokes Raman thermometry, which is useful for distributed temperature sensing, and I already talked to you about what are the different applications of that. Now let's move on to another aspect of distributed sensing. I told you about Brillouin scattering, right? The Brillouin scattering is essentially interaction of light with these bulk phonon modes inside the material, which are called acoustic phonon modes. That's just to differentiate that from the optical phonon modes that is contributing to Raman scattering, which is basically molecular vibration. Here the entire glass matrix is vibrating, so that's what we call as acoustic phonons. So how is this interaction working out, and what can we learn by observing this Brillouin scattered light? That's what we're going to look at next. So let's actually look at a cross section of a fiber. Let's say this is the core of the optical fiber. I have an electromagnetic wave that's coming in, okay. That wave, as it propagates down the fiber, is going to interact with these acoustic phonons. These are these vibrational modes that are bouncing around in all random directions, and part of that light is actually backscattered towards the source itself, because this is a waveguide. It captures light within a narrow cone of angle that's backscattered. So some of the other light that's scattered is going to just escape off the fiber, but a little bit of the light is actually directed back towards the source itself. And this light can essentially the field corresponding to the incoming radiation and the field corresponding to the backscattered wave, they can actually add, and they can add constructively or destructively, and they might actually generate a standing wave pattern over here. Now, if you increase this intensity, then that standing wave pattern now is going to become with a higher amplitude. You have a higher amplitude in terms of the field, and there is a process of what is called electrostriction. Basically, if you have a high electric field across a material, it makes it compresses the material, right? It makes the material more dense, and correspondingly you will have change in the refractive index corresponding to the the constructive interference of these oppositely traveling waves. Okay, so does that resemble something? Well, this is what we looked at previously as fiber Bragg gratings. Those are actually permanent changes in the refractive index that are inscribed in the fiber, but in this case it's not a permanent change in the refractive index. It happens only when the pulse of light is there, it's covering this region, and as the pulse goes away, this grating is going to vanish from this location, but it's going to form in some other location and so on. But like I said, if there is enough intensity coming in, you could actually have a strong interaction with the backscattered light, and through that's mediated by this grating that's formed, and so you'll have a stronger backscattered signal that you get from this, and this backscattered signal is going to be downshifted in frequency. Why is it downshifted? Because this grating is going to move in the direction of your optical wave, but it will move only at a slower speed. It corresponds to the acoustic velocity in this material. That's what VA is. So it is like having some sort of a Doppler effect, like a wave is going towards a moving mirror, right? The mirror is moving away from the wave, then it ends up like stretching the wave, and the backscattered light is going to have lower frequency, longer wavelength essentially, right? So that backscattered frequency, the frequency shift that you get, is proportional to the acoustic velocity. Okay, so that is actually a very important aspect. Why? Because the acoustic velocity depends on the density of the inherent material density itself, and the density of the material, this glass medium here, is going to change or is going to respond to changes in strain or temperature. Okay, so whenever there is a change in strain or temperature, the density of the medium changes. If the density of the medium changes, the acoustic velocity changes, right? And if the acoustic velocity changes, then the corresponding backscattered frequency, that is changing. Okay. So contrary to what we were doing with Rayleigh backscattered signal and your Raman backscattered signal, where we were essentially making an intensity measurement, in this case what I want to do is to make a frequency measurement. Okay, specifically I want to extract this frequency nu b. Okay, so if I look at the backscattered frequency as a function of time, and that time can be converted to position just knowing the velocity of light in this medium, then I can actually get a perturbation map along the length of the fiber. So this is what happens. So you have basically, once again, you send a pulse of light, but the pulse of light is essentially because of this Brillouin scattering is creating a temporary grating, and that grating is going to back reflect this is going to create this Brillouin backscattered radiation, which actually carries this frequency information, right? So the frequency will now be whatever the local, it's going to be dependent on the local acoustic velocity, which is dependent on which is dependent on the density of the medium, and that is dependent on the strain or temperature at that particular point along that medium, right? So this is what we are looking at now. By looking at frequency as a function of time, you are looking at strain or temperature as a function of position in this fiber. Okay, so this is how the final map is going to look like. This is actually intensity axis here. This is the length of the fiber. This is the start of the fiber and the end of the fiber. And this is actually looked upon at different frequencies, the backscattered signal frequencies. I won't go into the detail of how we extract these frequencies. That can wait. But you essentially get a map like this, where this is the Brillouin frequency corresponding to an unperturbed fiber. So all along the length of the fiber, all these regions, there is no perturbation, but there is one section where there is actually maybe an event, maybe the fiber is getting strained, or maybe the fiber is exposed to some hotspot along, let's say, a power cable. There may be a hotspot. And that will constitute a change in the backscattered the Brillouin frequency. Okay, so by looking at the shift in the frequency, you actually figure out what is the magnitude of the perturbation that the fiber is experiencing. Okay, so this is the concept of Brillouin based distributed fiber sensors. And this is useful for both strain as well as temperature sensing. I've talked about a bunch of different solutions as far as fiber sensors are concerned, but there are some, having the technology is just the beginning. Now when you want to implement it for a real situation, there are a lot of challenges. For example, let's say this is a bridge you have, and you need to look at the strength of this bridge, if there are any cracks that are developing in this bridge, right? If you want to do that, then you need to incorporate sensors all along the length of the bridge. Then the question is, do you want to use a quasi-distributed point sensor like a fiber Bragg rating sensor, or would you want to go for a distributed sensor? Would you want to go to a phase modulated sensor like what we talked about with the hydrophone and all that? So you have a bunch of solutions available. Then you need to decide which one is the best suited for that. You need, and for that you also need to know where should you incorporate these sensors. Where are the specific points? You may say that all these points which are well supported are less likely to develop cracks, whereas the middle region between these two supports, that may be a region where there's more probability of having a crack. So you may want to put a sensor there, or if you cannot decide where to put the sensor, just do a distributed solution. Just have a fiber all across, and then you can get the entire map, the strain map along the length of the fiber. And of course, some of the things that we talked about for the Brillouin sensor, for example, it's sensitive to both strain as well as temperature. So how do you discriminate between strain and temperature? How do you know it's one, if you see a shift in the frequency, how do you know it's only because of strain? How do you know it's not because of temperature? So you have to come up with some ingenious methods to do that discrimination, and those are the kind of challenges that we will look at as far as this course is concerned, and see how to address them. So let me just summarize what we talked about. We talked about optical fiber sensors gaining widespread acceptance, and it's really rapidly becoming the technology of choice for physical sensing, and that's because of the fact that optical components are becoming a commodity thanks to all the excellent developments in optical communications. But all said and done, we have a variety of solutions, but finally the implementation is going to be the key, and that requires ingenious engineering, and that's exactly what we are going to do in the course. We're going to try to develop you as better engineers that could make better decisions, and you could come up with good solutions that are useful for a lot of practical applications. Okay, so we will meet further to go into details about a lot of these things in the subsequent weeks. Thank you.